Hello, linear algebra student. This video is for chapter 4.1, part 2. So the second topics that we're going to talk about here is subspace. In part 1, we talk about what is the meaning of a vector space. It obeys 10 axioms together with sum and also scalar multiplication. And a subspace basically is if we have a vector space that we know already being a vector space, and then we have another set called H. So H is a subset of V. We can prove that this set H it will be a subspace if it obeys three properties. So these three properties is zero actually is part of this subset. Second is if you add them together, it's still within H. If you add two vector that's in H, it's still in H. We call this property closed. Closed means whenever you add two vector inside the subset is still inside. The third is H is closed also under multiplication by a scalar. That means if you multiply any scalar in the real number in any of the H in any of the U in H, then C times U is still in H. So it can be shown that this is a vector space because it still obeys the 10 axiom. So let's look at the review that 10 axiom. So if you have a set, and of course you will have the definition of sum and the definition of scalar. If H is part of a subset of a vector space, so this two is already done. And then U plus V plus U is still the same. U plus V plus W, associative property is still the same. So and then all these scalar multiplication properties, 7, 8, 9, 10, should still be the same, right? Because H is part of a vector space. So that's why the only thing that you need to prove is zeros. And also when you multiply C to it, it's still not just in V, but in H. So we need to prove this one, and also the first one. That is closed. That means when it is you add two vector together, it's still inside that subset. And we can say so that's what we say. We say number 1 and number 6 by definitions is how we define sum and scalar. Number 2, 3, and also number all those 0, all the 1, and all those should be okay, right? Should be okay here. So 1, 2, 3, so 4, we don't know, so that's why we need to show that 0 is in H. So if 4 and 5 are okay, then this should be okay. So 7, 8, 9s are just by default okay. 7, 8, 9, 10 actually. 7, 8, 9, 10 are still okay because if UV is in H, so UV is still in V, right? So the only three things that we want to make sure is U plus V is not just in V, but is in H. So we need to prove it. And also, so if it obeys this, then it would be in V. And we also need to show that 0 is in H. Because otherwise, 0 plus U will not be in H. And the third one would be C times U or V is in H. If they're in H, then it will be in V, so all the 10 axioms is satisfied. So we would look at some definition of sets of subspace to see if they are sets of subsets in a vector space to see if it is a subspace. First one is the zero subspace. So this space only have the zero vector. Does it make sense that it is? So because it has only vector, so sum doesn't apply. So 0 is already in there. So the three properties that we have, 0 vector is in, this is satisfied, A is satisfied. It should be closed because 0 can only add to 0 and it's still 0. And anything multiplied to 0 is still 0. So the three statement is satisfied. Number 1, 0 is in H. Number 2, 0 plus 0 is still equal to 0 is in H. Number 3, if you have any number C times 0 is still 0 and it's in H. Right, so we need to prove this. So this is a subspace. Second one is all polynomial with degrees at most n is a subspace of all polynomial. So first of all, we have to show that 0 polynomial is in H. Yes, because 0 is at most, the degree is at most n. The second one is 0 plus 0. Oh no, if I have two polynomial of at most h, so p of t plus q of t, most of them, like both of them is at most h, so this combined like terms, so the degree is also at most h. And then if you multiply c times p of t, the degree is also still at most x, at most n. So it is belongs to H. So it is a subspace. The third one is the vectors in R2 a subspace of R3? So R2 is, if I have a V in R2, it would be V1, V2. This particular vector is not even in R3 at all. So V actually, R2 is not a subset of R3, so it would not be a not a subspace of R3. It has to be actually exactly like 3 number to be in R3. So you can say maybe if I have V1, V2, 0, maybe this one will be like if I have a set of vector, not R2, but kind of like R2, but with 2 numbers, that is, real numbers on any real number. So this may be a subspace of R3. Okay. 4. Can a plane that does not go through the origin of subspace? So of course not. No. Because if it doesn't go through the origin, then 0, 0, 0, which is the 0 vector, is not in H. So it's not a subspace. Subspace must have H. Must have 0. The next things we want to talk about is theorem 1 about span. Okay, we in chapter, I think 1.4, we talk about the word span. Is about like if I have some vector, really just vectors. And then if I do linear combination of all different linear combination as form a sets, we call it the span of V1 to Vp. So here we apply the same, same idea, but the vector that we talk about is the vector space V. So these are not just the vector that we talk about from Rn. They are actually just really vector. It could be a polynomial, it could be a function, it could be a, sequences, and they are subjects in a vector space. The span of them is a subspace. So anytime you can find some vectors and you span them, it automatically becomes a subspace. So and the subspace that is spanned by this is called a spanning set for H. Spanning sets. So if you have a set and you use some vector to span it and you make a subset, this subset is called a spanning set for H. Why is it a subspace? So we just have to check 3 things, right? First thing is 0 is in this is in H. Why is 0 in H? Because if I do spanning, I can choose any linear combination including zeros, because 0 V1 plus 0 V2 plus all the way to 0 VP would be in H, right? It is a linear combination, so 0. 0 is in H. The second is if I have two V1 and V2, when I add them, they should be in H. Oh, not in H, because it is a linear combination. Span, the meaning of span is linear combination, a particular linear combination. Anytime you have a linear combination of two vectors, that would be in the span. So in particular, any V1, V2, you add them, it is still in it. And if it is not, if you have vector that is not one of these, they must be a linear combination of V1 to VP, and then you can just add them together. The third one is a multiple, any multiple of V1 would be in it, because this is in X, because this is a particular, also a linear combination, right? Linear combination means multiply any scalar. So this spanning or linear combination definition of spanning actually is similar to what you declare a vector space or subspaces. So that's why anytime you can choose some vector and you span it, you would be the set that you span automatically is a subspace. For example, example 1, I have a set of H and it contains some vector 2a plus 2b and b, where a and b is in R. So I have anytime you look at this vector is always 2a plus 2b for all the different one of a and b. So show that it is a subspace. To show that it is a subspace of R2, because these are vectors of 2, to show a vector with a subspace, we have to check these three normally. But because of this theorem that we have, theorem 1, that if I can actually find a spanning set that will span this, then automatically it is a subspace, because that's theorem 1 say. Theorem 1 say if you can actually write H being spanned by some vectors, then your H is a subspace. So that's the power of theorem 1. Spanning itself actually guarantees these three properties of subspace. So let's try to find the spanning vector of H. So I'm going to write any vectors in H like this, kind of like how we write the parametric solution. So we'll factor the A out and we'll say, oh, that is equal to 2 and then 0. Plus b, factor it out, plus 2 and then 1. So any vector v can be written as a times 2 0 plus b times 2 1, because that's how you define your H, right? If v is in H. So that means any v in H is a linear combination of these two vectors. So you can say that H is equal to the span of what? Okay, here we say AB in real, right? So H is the span of 2 0 and 2 1. So there you have two vectors span it, so H must be subspace by theorem 1. Okay. Example 2. So we don't have to we don't have to prove these three things, so long as we can find the spanning set. H. Example 2. If H, okay, I think we don't have enough time to go through this, so we'll do this example in the third reading.